Hello guys, how you doing? I'm Rahul and you're watching the Concept Builder. And today guys, we are continuing our heat transfer topic part 2 over here. And I hope that you have seen the first part, okay? And so let's get started. Okay, so in first part we saw this equation and we got the derivation of this equation. We derived this equation and we saw application of this equation for cases where the area is constant. So this equation is applicable for a slab, okay? And we also saw that what will happen if the heat is being produced in it, and what will happen when there is no heat generation and there is steady state, okay? So this condition all we have seen, but now today guys we're gonna look at the case where there is variable area. Okay, so area will be changing, and the best example for this is a cylinder and a sphere, okay? And when the heat transfer is taking place radially, okay, so if this is a cylinder and if you see the front view over here, suppose it has some thickness, okay? So it has some thickness and the radius, inner radius is r1, the outer radius is r2, like that. And so if you see the over here, the area will be changing, because the area over here, if we talk about the area, it's gonna be pi dl, okay? And or also you can write it as 2 pi rl, okay? So this is the area of a cylindrical surface. I'm talking about this area, okay? This area is 2 pi rl, okay? And the heat will transfer from here to here in this direction. So area will be the area which is perpendicular to the motion of the heat. Okay, so we will take we are taking this area, and the formula over here is 2 pi rl. So if you see that when we'll go from here to here, okay, the r will increase and the area will also increase, okay? So here comes the one concept come over here, is that what will happen to the flux. Okay, so what is flux? Flux is actually heat transfer rate, which will be in watt divided by area, okay? And you see that area increasing, that's why flux will decrease. But one thing over here, the concept is that the heat transfer rate in watt at steady state, it should be constant throughout the cylindrical section over here. That's why the flux into area, so flux into area will be constant, okay? So this is our first formula. That okay, so this is the most basic formula you have to remember, that the flux into area will be constant, because what is flux? Heat transfer rate per unit area, and if you multiply the area, what you will get? The heat transfer rate. And if the given that there is a steady state, then there cannot be any accumulation of heat, so whatever heat came in should go out. So suppose a shape like this, and heat is being transferred from this direction. So if area is a1 and area is a2 over here, and you will see that at steady state the flux will high at this moment, because the flux into area is constant. So if area will increase, the flux should decrease, like that. So there are many questions asked from this concept in the GATE exam also, so you must be familiar with this. Okay guys, so we have seen that for the constant area problem, there was the equation was like this, and if we have this equation, if we have this differential equation, we can do a lot of things with this, but in case of the variable area, and if we talk about cylinder and sphere, and this is a very special topic we have to do, because there are many questions from cylinder and sphere problems, most time the cylinder, Okay, so for this, which equation you should use, and in our exam point of view, they only ask for radial heat transfer. Okay, only radial heat transfer. So what will happen, there will be a cylinder which will have suppose internal diameter d1 or r1 will be the radius, whatever they tell us, and the outer diameter will be d2, something like this. So for cylinder sphere there is a differential equation, and I'm gonna write the differential equation formula, and that formula you have to remember. Okay, so this is the formula 1 divided by r raised to power n, where the r is the radius. Okay, so at any r you can find out, so this is the radius, and with the differentiation with respect to r also, and r raised to power n dt by dr, and again the same things. Okay, and this is for the radial direction only. Okay, so the heat should be transferring from in this direction only. Okay, from higher temperature to low temperature. Okay, so what is the value of n? Okay, so it's very easy actually. N equal to 1 for cylinder and n equal to 2 for sphere. Okay, so that's what we're gonna do. Okay, so let's make it easier, and let's first talk about a cylinder and what can we do about it. So if we put n equal to 1, then we get the equation for a cylinder. Okay, and we can assume that the cylinder has inner radius r1 and outer radius r2. Okay, and it is an hollow cylinder we are talking about, and it has a length of L. So this is it's actually a pipe. Okay, now we will take again the cases, and this time there is homework for you, and if I give you the case of steady state and Q generation equal to 0. Okay, and in this case you have to find the temperature profile, and I hope that you will do it, because if you have done it in your if you have seen our previous video, then you will be able to solve it, and you will be able to find the temperature profile. So just pause over here and try yourself to do it, and then I will show you. Okay guys, so I hope that you have at least tried to solve this, and it's very easy. So what we have given, steady state means this term will be 0, because in steady state there is no change with time, and Q generation is 0. So let's write our equation. What will be, so it's gonna be 1 by r d by. Okay, so I hope you have done it, and we can also write here del or d. There is no problem, because the heat is being varied, the temperature is being varied in only one direction. Okay, that's why you can use both of things. Okay guys, so you know that it's equal to 0, so r will become 0. Okay guys, so with this equation you will get after applying this condition, and if you solve it out like this, and you will get this equation. Okay, so it's very easy. So because differentiation of something is constant, that's why this should. Okay, so thus you can do it. Okay, I hope you have understood how we do it. So finally you get this thing, and if you just integrate it, what you will get, temperature will be. Okay, so this is gonna be your temperature profile. Okay, and what you see there is ln over here, so you should know that the temperature profile is logarithmic. Okay, so in objective question, if they ask you that what will be the variation of temperature when there is steady state and no heat generation, then the answer is the temperature profile will be logarithmic. Okay, and now I'm gonna tell you a very important concept, that how to find the heat transfer rate. So many times they will ask you to find the heat transfer rate to a wall, or heat transfer rate to a pipe, or through a spherical ball, or a hollow sphere, whatever they will give you. And in every case, only one thing you have to remember, only one formula, that heat transfer rate is equal to the temperature difference. Okay, the temperature difference they have given divided by the value of R. What is R? We have already seen. So if you remember the value of R for each and every case, you can easily find out the value of the heat transfer rate. So the now question is, what is value of R? And it's very easy. You can do the derivation as we have done for the previous case over here, and easily you can get the values of the thermal resistance. So for a slab, you have to remember that the thermal resistance value of R. So for a slab, you have to remember that the value of R is L by Ka, where L is the length. Okay, so if heat is transferring in this direction, then length will be the L will be along the heat transfer direction, and the area will be equal to the this area over here of this surface area. Okay, and the K is the conductivity. Okay, so that's why is, and for the cylinder, or for a hollow cylinder where inner radius r1 r2, we have seen over here the R value is ln of r2 by r1 2 pi k l. L is the length of the cylinder. Okay, and here heat transfer taking place in this direction. Okay, and for a sphere also, if the heat transfer taking in the radial direction, then the resistance gonna be this thing. So here r1 r2 are also the inner and outer radius, and of course we are talking about a hollow cylinder, that's why there are two radius. Okay, and most of the time they ask for this condition only to find the heat transfer rate. So they will tell you that there is a spherical shell, and the inner temperature is maintained at T1 and the outer temperature is maintained at T2, and what will be heat transfer rate. So you can easily find the heat transfer rate. Okay, and now a very important concept, that what actually tells you that what will happen if you suppose take a wall of conductivity K1, and you attach another wall, okay, of conductivity K2, and one another wall of conductivity K3, and these three are joined like this. Okay, and here is a very high temperature, suppose 1000 degrees Celsius, and here is 25 degrees Celsius, like that. And if they ask you that at steady state what will be the heat transfer rate, okay, how to solve such formulas, such questions actually. And what if they tell you that there is a pipe, and you have of some thickness T1. Okay, it has some thickness, and you make an insulation over it. So, okay, so the insulation will be on the pipe. So there is a pipe, and you have done the insulation, and they ask you that now what will be heat transfer rate if the atmosphere temperature is T2 and the inner temperature is T1, like that. Okay, so in all the condition, what the basic idea we use is that in our high school and in electricity chapter, we have seen that if there are two or more R's are in common, so R1, R2, R3, then we can make them in, we can add them, and we get the equivalent resistance. So there are three resistance values are there, then the equivalent resistance will be R1 plus R2 plus R3. And similar we can do it here, because here the temperature difference we can take from here to here. So here is 1000 degrees Celsius, here we have 25 degrees Celsius, and the heat transfer will be same, is steady state. Okay, so the heat transfer rate will be same from each wall over here. That's also an important concept. The heat transfer rate gonna be equal. So from heat transfer rate from here to, from air or of air to the wall, equal to the heat transfer rate from the first wall, equal to the heat transfer rate through the second wall, and all that, because we are talking about steady state, and steady state the heat transfer rate is equal. So that's you have to do. So the final formula becomes is that Q will be equal to delta T, which is the overall temperature difference, and if there are more than one more elements, so there are more than one elements are there, like there are 3 volts over here with different value of resistance. Okay, so if there are more than 2 resistance, then you have to use R equivalent. Okay, and if you are equivalent you use, and if the resistance are in series. Okay, this is the example of series. So in series you can simply r add the individual value of resistances. And here also, in the case of suppose there is insulation and there is the thickness. So suppose the r1 and the cylinder outer radius is r2, and we made an insulation over here, and this and then it becomes r3 over here. So you can find the r equivalent also, where it gonna be r1 plus r2. R1 is of the this pipe or a cylinder, and R2 will be of the insulation. Okay, and same formula for this, you will use this formula. Okay, for a cylinder, if it is a wall, then you will use this formula for, and if it is sphere, then you will have to use this formula. Okay, and now what if the condition is something like this? So there is a wall of conductivity K1 and temperature here is T1, and over here you have attached two blocks. Okay, two walls with this portion of conductivity K3 and this of K2, and here also one wall like this. So in this case, first of all, what you have to do is you have to draw diagram like this. It's your R1, which will be L1 upon K1 into A, and area we can assume the same for all the all the walls. Okay, R1 will be there, and here this will be case of parallel. So you can do it like this. Okay, and one more resistance of this wall resistance here, this wall resistance here, this wall resistance, like that. It's easy. And in parallel the formula is R equivalent 1 upon R equivalent. The inverse of R equivalent is equal to 1 by R1 plus 1 by R2. Okay, I'm talking about something like this. For this case, if there are two resistance are there, one is R1 over here, one is R2 over here, and for this case the R equivalent, you have to write this formula you have to use, and after this formula this thing will become something like this. Okay, so here it will become R equivalent. So in this formula what you have to do, first you have to convert this thing into a something like this. Okay, using the parallel formula, and when you will use this, your equation will become something like this. This is our first wall resistance R1 is your R equivalent from the parallel rule you will get from this formula, and R3, and now you have to add all the resistance and you will get the final R dash. Okay, you can call it capital R or R dash, whatever, and to find the Q you will have to use then delta T by R dash. So that's what you have to do. So if they tell you, if they give you like a lot of balls, they will ask you that there is a refractory over here, and there is a brick wall, and after there is some insulating wall, and here also some kind of paint over there, and like that, and they will give you different conductivity of this thing, and they will ask you that what will be heat transfer rate. So in this condition you should use this. So that's how we can find the heat transfer rate to a different type of arrangements. Okay, so now guys, next thing we gonna look at about what will happen if heat is being generated when the Q naught generation is not equal to 0. Okay, suppose there is a suppose there is a wire over here, and in the wire there is being heat being generated in the middle over here, and that's why how you gonna relate the temperature at particular value of R. So how you gonna relate the temperature R, and if it's like this, then at the center there will be the maximum temperature, right? Okay, and if you remember that the same case of the heat Qg not equal to 0, the same case we have done for a slab. So we took a slab and x equal to 0, we took x equal to L minus L like this, and we saw there was this kind of temperature profile was there, and in the middle there was temperature, maximum temperature. And if you remember that we wrote a formula for that, the theta upon theta max, where theta is the temperature at particular length minus out temperature divided by theta max is the maximum temperature minus the outside temperature. And that formula we got was 1 minus x square divided by L square. Okay, I hope that you still remember the formula. If you don't know about anything about this, watch our previous video, the first video that we have made on the heat conduction. Okay, so if you have this thing, so what happens over here, that in case of a cylinder, this formula is almost similar. Okay, so let me write. In the heat generation, what you have to do, first we have to define theta, which is theta is temperature at a particular R minus temperature of outside, and theta max is the maximum temperature at the center minus outside temperature. Okay, this thing we have to define. So in case of slab, the outside temperature is T0, and the TR is actually at temperature at any value of X over here. So for a slab, the temp TR is actually Tx. And why I'm using R, because now we're gonna look at about the when there is a cylinder and a sphere. Okay, it's not okay, so it's cylinder and it's a sphere, and the formula is almost same. So let's write the formulas. For slab, what was the formula? Theta by theta max. Okay, and for this we have done all the derivation, that how it has come so in our previous video. So I'm just writing the formula directly. So it's gonna be 1 minus x square divided by L square. Okay, you have you know what. And here remember most important thing, that theta max was equal to Qg. Okay, L square divided by 2 into K. K is the conductivity of this cylinder, slab. Okay, we are talking about the slab. K is conductivity of slab, and this is half length is L, or we are talking about S equal to 0 we took in the middle, and like this thing we have done so far. Now if we talk about a cylinder, then in case of the cylinder, the formula will be same, almost same, just the x will become r square divided by capital R square. That's very easy, right? So if you have the capital R over here and at small r, the formula and what is theta is Tr minus T0. T0 is the outside temperature. Okay, so temperature at the outside over here, just over here, this is a T0, and the maximum at the center there is the maximum temperature, which is T max. Okay, and at any value of R, small r, the temperature, if you want to know, then there is Tr. So it's basically temperature profile. But here also, what is the value of theta max? And the theta max value is gonna be Qg. Okay, is the value of heat generation. Here you're gonna capital R square divided by, remember, 4K. Okay, for slab it was 2K, for a cylinder it's gonna be 4K, and here was the capital L, here is gonna be the radius. Okay, and for a sphere also same, theta upon theta max equal to 1 minus small r square divided by capital R square, like this. And for theta max, here in this case it's gonna be Q generation divided with capital R square divided by 6 2K. Okay, 2K, 4K and 6K, and these three formulas are very important and you should remember, and it's easy to remember. So in the case they give you that heat generation, if they given, then you don't have to afraid, because you can easily calculate. So guys, these three formula you have to give remember, and another three formula were the value of thermal resistance. So if you know these three formulas, you have to remember anyhow, so that you can find the heat transfer rate. And you also know that what to do when this kind of composite walls are given. Okay, these are the walls made up of two or more than material with different conductivity. And if such cases are there, so what you can do, that how you can add the value of R and you can solve it. Okay, and also if the heat is being generated, then how you can use this formula. And this is shows the temperature profile, and they will ask you about this formula, that what will be a temperature at particular point at steady state heat transfer when there is QG heat generation. Okay, so there is a challenge that the first person who solve the questions and give the answer in the comment box, I will pin, and if the answer are correct, I will pin his or her comments forever.